So let's continue. Now let's try to note a bit the commands that we need on a certain page, and then we will look into how this is executed in a real hardware. So what is the first command that we have to have? To have a value from the memory position 13 in the cell 0. Any ideas? So the command that we need is this load command. So load the register R with the bit pattern found in the memory cell whose address is X epsilon. In our case, it is the position 13, and we want to load into register 0. So we can note here load the register 0 with the value found in memory cell 13. Ifunanya, I'm nearly not understanding you. I'm just seeing that you are talking. Now you're muted. So we are loading into register 0 the value of 13. Then load another value from the memory into register 1. So that's mainly the same. So load the register 1 with the value found in memory cell 14. Then in the next one, add the two registers and leave the result in register 0. So maybe we are just adding here that this is opcode 1. Add the two registers, assuming we have two complement data, and leave the result in register 0. So it's that one here. Add the patterns in register S and T as though they were 2's complement representation and leave the result in register R. So add. Then we have where we are leaving the result and the two values that we are adding. So we have here add, save in register 0, and save there the sum of register 0 and register 1. That's the command 5. Then the next should be store the result in another memory position at 15. So store the bit pattern found in the register R into the memory cell whose address is X epsilon. So that's command 3. So store the value from register 0 in 15.
Hello, sir. Hello, sir.
Hello, I'm not understanding you much, Dominic.
Yes, I have a question on the
I'm not understanding anything. I don't know, is your microphone maybe not working?
Now you can hear me. Now you can hear me.
Nothing. Can you maybe write in the chat?
Okay, I'll write on the chat.
So the last command is, of course, the halt execution, because our program has now finished. So load register 0 with the value in memory cell 13, load register 1 with the value in memory cell 14, add register 0 and 1, and store that in register 0, and then store the value from register 0 in memory cell 15 and end the program. So let's look into how this is looking like. So that's just, we will come to it later. So this is now the program, and this is the data. You see, we are storing both in the same memory. And we have the control unit, we have the arithmetic logic unit, and the arithmetic logic unit has the register 0 to F. It has an instruction register where it is storing the instructions. It has a memory address register, and it has a memory data register and a program counter. Now we have here our program, and we have it now more or less in a text written manner. What we have to do now is we have to create the operation code out of that. And so the opcode for the different functions that we have here, I forget for the hold, that's C. The opcode is 1, 1, 5, 3, and C. And then we have the operands. So for the load, we have the register where we want to store the value and the address cell from where we want to load the value. So here we are storing in register 0, and we are getting from cell 13. So our total command is 1013. Let's maybe mark with some colors here. So that's the load. That's the register 0. And that's the memory cell 13. And now for the second one, it is similar. So load into register 1 the value from memory cell 14. Add now, that's the command. Store the result in register 0 and add register 0 and 1. Then store 3, the value from register 0 into memory cell 15. And the hold command is just C000. There are no parameters that you are handing over. So the question is, store the result at position 15. It means the position 15 is empty. We don't know. But if there is something, we are overriding it. So we don't know if position 15 is empty. And therefore we don't know. Okay, can you repeat? Of course. So we noted here the command in textual form. Then we noted the commands not in text, but as text or as number instructions. So load has the operation code 1. That's what we have here. That's the operation code. And then the parameter or the operands for the load register are Rx epsilon. So register R, load the register R with the pattern found in memory cell X epsilon. So we are loading the register 0 with the pattern found in memory cell 13. Then we are loading the register 1 with the bit pattern found in memory cell 14. Then we are adding We are storing the result in register 0, and we are adding register 0 and register 1. So those two. Then we are storing the value from register 0 in memory cell 15, and then we are ending our program. And now, of course, there is a question, but the commands shouldn't be represented in binary. Yes, of course they should. So now we have the decimal numbers, and we can, or these hexadecimal numbers, and we can translate these hexadecimal numbers into binary. And therefore, let me just move this here a bit. Let's make it clearer. So what is 10 in binary? No, sorry, 13. It's the whole number that we are integrating. Oh no, it's 10. And we are always using 8-bit for it. So like that. So 10 is 000100. Just put the calculator once more. So let's continue with the slides. So in the next step, what we are doing is we are translating our textual commands into these numbers as we just did before. So 1013, 1114, 5001, 3015, C00. These are our commands. And we just have some values in the memory cells 13 and 14, namely 4 and 2 in decimal manner. Now we are translating all of that into binary. And therefore, we need more than 8-bit. We need 16-bit. So we need 8-bit for the first and 8-bit for the second, because we are going up to FF theoretically. It's in hexadecimal. And then we are getting those binaries number. And here you are now seeing, here we have the lines 00, 02. Here we now have two lines, so 02 and 03, and 00 and 01. Clear? The step from the last slide to this slide. So we are translating each value. Let's maybe do that by hand once again. So 1 in binary is 0001, right? 0 in binary is 0000. So let's mark once again. This is now the 1. This is the 000. Then another one, 0001. And 3 is 0011. So that's now the first line. Clear? So we are now representing these hexadecimal values as binary values. Can you repeat, please, how we determined add register 001? So let's look in the add command again. Add the bit patterns in register S, the second position, and T, the third position. I thought they were 2's complement, and leave the result in register R. So first I'm mentioning where to leave the result, and then I'm mentioning what to add. So what is written here, again, is R is S plus T. And that's what I have here as well. So I'm storing the result in register 0. And what I'm storing there is the value of register 0 with the value of register 1. Clear? And now we are translating all of these commands in binary. Let me, okay, here for some space maybe. So the next binary command would be 1, that's 0001, 0001, 0001, 0100. Nice. Then 5 is 0101, 0000, 0000, 3 is 0011, 0000 is 1, and 0101 is 5. And C is 1100, 00000000000000. So these are now the commands in binary. Let's maybe mark them here as well. For one example, that one here, that's 3. That's 0. That's 1. And that's 5. So we are translating from text to hexadecimal to binary. So the question, why is the result of register 0 and register 1 equals to register 0? It's not. I'm storing the result of the operation register 0 plus register 1 in register 0. So it is, if you would write that with variables, you would write here A is equal to A plus B. And now A is, for example, 5, B is 7, so the result would be 12. So now we have that in binary. And even the data is stored in binary, because in the PC, we are storing everything in binary manner. Now we have to look into how is our CPU processing that. So first of all, it fetches an instruction from the memory at the address pointed by the program counter and stores this instruction in the instruction register. So we have the program counter. If the program counter is at 0, it is taking the command at address 0 and stores it in the instruction register. Then increment the value stored in the PC, in the program counter, to point to the next instruction in the sequence of instructions to be executed. So in our case, by 2 counts as our opcode plus operand have 2 bytes. Then decode the instruction in the instruction register to determine the operation to be performed and the addressing modes of the operands. So you're decoding what you have the instruction register, then you're calculating the values needed to determine the locations of the sources, operands, and the address of the destination. Then you're reading those values, you perform the operation specified, and store the result in the designated location. And then you are going to step 1 and doing the same what for the command which is stored in register 2. We will see on the slides how we are executing the code that we have developed in binary manner. But what we are doing is we are fetching the code, then we are decoding and executing. Then we are fetching, decoding, executing. So we are executing or running the machine code in this circuit. So let's look into the machine code that we have. That's that one here. So this is the code that we have developed now in binary manner. Now, in the step 0, our program counter was at 0. So we loaded this command into the instruction register. Okay. So let's maybe use some colors here again. So the command, you remember, was the add. Or load, sorry, it was load. Let's look into it again. So load register 0 with the value of memory cell 13. So this is the command that we have here. Load register 0 with memory cell 13. So we are loading into register 0 what we have in memory cell 13. So that's memory cell 13 to register 0. In the memory address register, we have 001, 0011. So that's 13 here. Here we have the memory address register from where we have to load. And here we have the memory data register, which is our value 4. So here we have 4 and here we have 2. Okay, so here we have the command in the instruction register. Here we have the address of the memory. And here we have the value at that address. And we have increased our counter to 2, which is the next step. So let's maybe mark here once again. The first one was load register 0 with 13. With the value found in address 13, not with the value 13. Then load register 1 with 14. Add, store in register 0, and add here register 0 and register 1. Store the value of register 0 in memory cell 15 and halt. That's the code that we have here. Now we are going to the next step. So that was step 0. Now we are going to the next step, step 1, which is that one here. And that step was load the value from register from memory cell 14 into register 1. So it was that command. That we are storing in the instruction register. We have here the memory address 14, so 1, 4, and the value there is 2. So we are loading the value which is found in memory cells 14 into register 1. And of course, we are increasing at the end the program counter. Then we are going to the next step. Step 2, which is now code 4 and 5. And in that one we have 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, which we are loading into the instruction register. This instruction says to add the values we have in register 0 and register 1 and store that in register 0. So here we have now 6 because we have register, or we had register 0 with 4, register 1 is still 2, so we have here for register 0 4 plus 2. And you see we do not have anything in this case for the memory address register or for the memory data register, because we are only working with the registers. We are not working with the storage for the moment in this step. So they are empty, and we have again increased the program counter for the next step. The next step is now step 3. Which is 6 and 7, and that was storing the value from register 0 into memory cell 15. So that was the command, which is in the instruction register. And the command said, we are now storing the value from register 0 in memory cell 15. So here we have the 15 for the memory address register, and the value that we have there is 6. Why does it not draw the line like I want? There is still something in register 1, but we are not caring about what is in register 1. And now we are again increasing our program counter. And the last execution that we have is just the halt execution. So the step 4. Wait, 9. So what we have now in the instruction register is that one. And therefore we are not caring about registers or memory address register or memory data register. We do not need that for this step. So let's review again. So the first thing, we are loading, or we have loaded what was in memory cell 00 and 01, of course, into the instruction register. So that one here into the instruction register that says load into register 0 the value from memory cell 13. So here we have the memory cell, and that's the value in memory cell 13. So we are loading register 0 with the value 4, because that's what we have in memory cell 13. Then we are loading register 1 with, so load register 1 with the value which is in memory cell 14. In memory cell 14, we have the value 2, so we are loading here 2. Then we are adding what is in memory cell 0 and 1 and storing that in memory cell 0. So we have here 4 plus 2 is 6. Theoretically, you can also store that in another memory cell, but then, or in another register, but then you need 3 instead of 2. And the last command is now saying store what you have in register 0 in memory cell 15. So that's what we are doing. In register 0, we have the value 6, and we are storing that in address in memory cell 15. And then we are ending the program. So this is how adding is executed on a microcontroller as machine code. If you are programming that, you are programming like that. That's interpreted as a hexadecimal code, which is stored in a binary manner, and then executed by fetching the code, decoding it, executing it, and redoing that. Is that clear? Or do you have questions to that? Okay. Then let's just review once again. So the first, from Neumann principle, data and program are not distinguishable. They both consist of 1 and zeros. That's what we have here. It's just 1s and zeros, and they are stored in the same memory on different addresses, but stored in the same memory. Data can, it is used a program if it is fetched into the instruction register and then interpreted. That's how you are separating the zeros and ones which are representing a program from the zeros and ones which are representing data. Data can therefore turn into program code if the program counter approaches fields containing data. So theoretically, we are here now at 10. That would be 10 and 11. If you are on it, then at 12, you would interpret what is in memory cell 13 here as program, if your program counter is continuing. So you somehow have to know where you are storing the data and where you are storing the program. But you are not storing at different places, just in different memory cells. And of course, if you are interpreting the data as program or vice versa, then you can have random actions that you cannot understand because you're just wrongly interpreting the ones and zeros that you have there. So this is how an assembly program is executed on a microcontroller or on a controller in general, on a CPU, in a very, very simplified manner, because as we saw in the data sheet, there are much more commands to realize functions. But here, just to give an understanding of how this is working, we will rely on this simplified version of the code. And now the last subchapter in our chapter 4 is about algorithms. And therefore, first of all, we have to see what is an algorithm. So an algorithm, therefore you have to note that the definition requires that the set of steps in an algorithm be ordered in terms of the order of the execution. An algorithm must consist of executable steps. Computer scientists use the term effective. That is to say, a step is effective means it is doable. So you can execute that. The information in the state of this process must be sufficient to determine uniquely and completely the actions required by each step. In other words, the execution of each step does not require creative skills, and there is no element of change. So if you are redoing a certain algorithm, the result will be always the same. So you know maybe that there are some random number creators on the web or programs which are creating a random number, right? I guess you can even type in at Google just random number. Just check. Random number generator, yes. Let me just reshare my screen. If I'm finding where to do, I have too many windows open with the chat and tab seeing you. So if you're going here to Google and you're typing in random number generator, then you can set there a min and a max value. Let's pick 1000 and generate a random number. And you see it's any value between 1 and 1000, and it's generating that randomly. But if we are now coming back to our definitions here, an algorithm means that you are not having any creative skills, so there is no element of chance. But in a random number creator, we just assume there is, but it is not, because that's not a random number like you would create if I'm asking you to think on any number. There is a formula behind which is calculating that number, and it is becoming random, for example, by adding into this algorithm which is creating the random number something like a time and a date, which means the result that you are getting depends on the time and the date. And by that, as the date is something unique upcounting, the chance that you are getting at the same time, the same date, the same number is 0, because you're adding the other date. It is not really a random number. That's really a calculated number, and there is a formula behind that. But this formula is including something which is not obvious, like date and time, or I don't know, maybe the position on Earth that you're sending this request from, or things like that. But it's a calculated number, because if not, it wouldn't be an algorithm, because an algorithm does not have any element of chance. And eventually the execution of an algorithm must lead to an end and should be as generic as possible. And then you see there an algorithm is an order set of unambiguous executable steps that defines a terminating process. Now let's look into a simple algorithm, an old coffee machine. And of course, if I'm asking you how to operate that, for sure you know that first of all, you have to place the filter before you're filling in the coffee, and you have to fill in some water before you're turning on. So you know somehow the algorithm, how you have to make a cup of coffee using these machines. And on the right, you're seeing, so lift the lid for the filter basket and water reservoir access, insert a mist of coffee, 4-cup paper or permanent filter into the removable filter basket, then add desired amount of coffee, referring to the coffee measurement chart, fill the decanter with cold water, pour the water in the water reservoir, plug the cord into the electric outlet. After contents have cooled and turn on. So theoretically, you can even plug into the electrical outlet before you're filling with some water. But the manufacturer is describing like that. So the first thing that you're doing is you are placing a filter. Then you are placing the coffee. Then you are placing the filtered water. Then you are plugging in and turning on. You are not plugging in, filling the water and filling the coffee, which would also work, but the algorithm they defined for that is that one. If you're doing that differently, then you're just not following the algorithm. But in this algorithm, there is no element of chance. There is a clear order on how you have to perform the steps. It is defined how you have to do that. And that's an algorithm. Another thing would be a programmable calculator. So here you are seeing a very old one from 1978. By the way, the first programmable calculator that was available on the market was an Hewlett-Packard 65. What would you assume how much it costed? That was, I guess, in 1975, so just 3 years before. What would you assume what a programmable calculator costed at that time, adjusted for the purchasing power that we have today? Someone wrote, what, 10,000 US dollar? And that's not far from the correct answer. The correct answer is 4,400 US dollars. So if you're buying a calculator nowadays, that's costing, I don't know, 20 euros. If you would have bought one in 1975, a programmable one, of course, not a cheap classical one, a programmable one, that would have costed 4,400 euros. Much, much more than a high-class notebook. And you can see there, for example, in this list over there, it came with a sheet of paper where some algorithms had been defined. So, for example, the code 45 was calculating pi. So there was a function stored at code 45, which was calculating pi. And there had been empty keys as well, or empty codes. So empty cells where you could store a program, where you could store own algorithms. So, you know, for calculating pi, there are different algorithms how you can do that. You're never getting exactly pi because pi is an infinitesimal long number. Therefore, you have some algorithms which are calculating pi roughly, I don't know, up to 1,000 positions after the comma, or 100 or 50 or whatever, depending on how accurate you want to have it. And you can store such an algorithm in a memory cell and address that with a certain code. And there are empty memory cells and therefore you can define own codes to access algorithms that you were defining by your own and storing in that computer. So something that you would do nowadays with MATLAB, for example. And how such an algorithm is looking like in a general manner, not in a certain programming language, just in a general manner, is like that. So usually you have a name for the procedure, which gives an algorithm a name so that it can be referred. Here you do not have a name, here you have a code for the algorithm. But in general, you usually have a name, then you have some parameters that you're handing over, so input and output parameters. That's the interface of your procedure, of your algorithm. Then you have an assignment, which is saving off computed values, not using the address in main memory, but a symbolic name. So usually in your algorithm, you're not using an address like we did, the memory cell 15, because that's something your compiler is handling for you if you're programming. And then you have some selections, for example, an if or a while or whatever, where a condition has to be fulfilled. So if the condition is fulfilled, then execute something, or if the condition is fulfilled, then execute something, and if not, then do something else. So either this or that. And while means, so while a condition is true, do something. So I don't know, while the time is between 8 o'clock in the morning and 8 o'clock in the evening, turn the lights off. While not, turn it on. Things like that. You can do it for a while. And what we have here is now something called a pseudocode. So you're writing a kind of code to describe an algorithm, but you are not writing the code in a certain programming language. You're writing it in a general manner. So again, the planning, you're writing that in a certain way of planning in the pseudocode. And then with this pseudocode, a programmer, so a craftsman, can build the function in a certain programming language out of. But here you're still developing the algorithm. You're not programming here. So then how can you represent such an algorithm? There are different ways. Maybe you are starting with something text-based. So as long as the value of neither x nor epsilon is 0, continue dividing the larger of the values by the smaller and assign x and epsilon the values of the divisor and remainder, respectively. The final value of x is the greatest common divisor. Do you remember? That was the very first example we did in the first session of our informatics lecture, finding the greatest common divisor. And here is the algorithm how you can do that. So as long as the value of neither x nor epsilon is 0, you're dividing the larger value by the smaller, and you are assigning the value of the divisor to x and the value of the remainder to epsilon. And you are doing it as long as x or epsilon is not 0. So that's now in written form. Now you can create out of that a flow chart. So you are starting here, you have two values m and n. If n is larger than 0, if not, then you are writing m. If yes, then the remainder is m mod n. So the remainder is the rest if you are dividing m by n. M is then your n, and n is your r. Then you're checking again, is n larger than 0? If yes, then you're repeating as long as n is becoming 0, and then you are printing m as the greatest common divisor. Another way of representing that is the so-called Nasse-Schneiderman diagram, and you see that's already looking like some written code. So you have there some tabs used somehow, you're reading, then you have here the while loop. which is repeated as long as n is larger m. And you have the commands like you have them here in the flowchart as well. In the next step, you can write that with some pseudocode. So the name of the procedure is Euclid. The parameters, so the interface of your procedure is m and n. And then the content of your procedure is while n larger n do, r becomes m mod n becomes n, and n becomes r. And if you are not in the loop anymore, then you are returning m. And here you are now seeing the implementation of this algorithm in Visual Basic code. So you have a function Euclid, and the parameters are m and n, which are integers. You're dimensioning in the function r as an integer, and while n is larger than 0, you're doing these calculations, you're closing the loop, and if not, your Euclid, which is the result of your function, is n. And now let me just show you that one in Python. Come on. Seems to be starting very slow. I don't know why. But it is starting. So maybe let's just continue meanwhile with the last slides while it is starting. I don't know why it is that slow. So the last thing that we already mentioned in one of our first lectures was this Gödel's incomplement theorem, which is stating that any complete study of our arithmetic system lies beyond the capabilities of algorithm activities. And there is a visualization of this Gödel's theorem, I guess we already saw in the beginning, that you have here two statements. And the first one is stating that the statement below is false, while the statement below is stating that the statement above is true. So that's now incomplement, because if that one is true, it means that that one is false. So here it says the statement above is true, and the statement above says that the statement below is false. So if now that one is true, that leads to the fact that that one is false as well. And that's the Gödel's incomplement theorem with the problem of self-referencing. So, and now meanwhile, also my Python started. And let's just come back to, I don't know, maybe that one here. And I will just share my screen differently. So here is now this greatest common divisor realized with Python. You see here I have defined m and n with certain values and have defined a function, so an algorithm called Euclid. The interface of it is m and n. Sorry. Let's make it like that. So m and n. And now I'm first of all calculating the absolute values in case they would be negative, while n is not 0. So n larger than 0 means it is not 0. My remainder is m mod n. So this percent sign is the mod function in Python. Then my m is becoming my n, and n is becoming r. And if the first condition is not fulfilled, I'm printing m. Because m is then my greatest common divider. So if it is not fulfilled, write m. And that's the end of the function. And here I'm calling this function Euclid and handing over m and n. Be aware that's a capital M and a capital N. And here we have just a small m and n. And here you have again a function that I'm calling from the math library in Python, which is called GCD, greatest common divider, which is calculating the greatest common divider as well, but as an implemented function. So a function which is implemented in a Python library. And if I'm now executing here the code, you're seeing the greatest common divider of 155 and 72 is 1. Once calculated by my self-created function, once calculated by the implemented function. And if you're changing the values on a node to 60 and 20, then the greatest common divider is 20. And usually you are not starting with writing down here a code. You are usually starting, first of all, to describe in a textual manner what you want to have. Then you are trying to structure that with a flowchart or such a Nasse-Schneiderman diagram. Then you can create a pseudocode. That's still the planning phase. And then you're either going to someone who knows how to code VBA, or you're going to someone who knows how to code Python, or you're going to someone who knows how to code C#, and they will then create out of your pseudocode respective VBA code or Python code or C# code. So again, usually, as we saw it in the introduction to the lecture, very, very often, if you're talking about informatics, it's programming what is coming in our mind. But this is just a very, very small part of informatics. It is much, much more important and even much more brain work to create these algorithms, to describe them such that they can be programmed and such that they are fulfilling the requirements for an algorithm. Okay, that was the theory for today. After the Christmas break, we want to do some examples on this machine code and then the mock exam and the review session. Do you have any questions to what we did today? Let's just look in the chat. If not, then in case you are celebrating Christmas, I'm wishing you Merry Christmas, and we are seeing each other after the break. Thank you, and see you. Bye-bye.
Hi, Merry Christmas.
Thank you.
Merry Christmas.
I have a quick question.
Mhm. Just let me change my loudspeakers. I'm not understanding you much, Mohammed. I don't know why. If it is my system or something else. Just 1 second. Can you say something?
Yeah. Is it better now?
Again, please.
Is it good now? Is it better? Can you hear me? Hello? Hello?
Just 1 second. Again,
Hello?
I'm not hearing anything. Maybe now.
I'm currently speaking. Can you hear me?
Yeah, now it's working.
Okay. So regarding the exam,
Uh-huh.
are we gonna have like a mock exam or anything like that?
Yes, I said at the beginning of the lecture and 2 minutes ago that we will
Okay.
have.
And because like I'm on, it's not my first attempt, so I'm just trying to understand how it's gonna be like this semester, because this is like the first time uh, uh, with with you having this topic. So yeah, is it like it's gonna be a different type of exam or maybe
So
something?
we will, the plan for the remaining semester is that now the first session after the Christmas break, which is on the 10th, we will do some exercises on this machine code. Then the week after, we are doing the mock exam. But again, the exam itself will only take place in presence in Pfarrkirchen. So
Yeah.
therefore, you have to be in Pfarrkirchen to participate to the exam.
Yeah.
And therefore, my request is also, if you're participating to the mock exam, to do that on Thursday in presence, because then you have even the surrounding like it will be in the exam. So you will be in the classroom, you have 90 minutes. We will try to do that online as well. And then in the last week of lectures, we will do like a review session. So if you have any questions or if you want to review something or whatever, then we will do that in the last week of the lecture.
Yeah, thank you. And regarding like the template or like for the exam, is it also like gonna be 9 questions or so like class T, or it's gonna be look different in other ways?
So the exam will be, there will be some theoretical questions where you have to describe something, where you have to show that you understand what we did. Some number transform system, some binary stuff. So I will try to cover what we did in the lecture within the exam.
Yeah, okay. Sounds good. Thank you very much.
You're welcome.
Hello, sir.
Hello.
Yeah, now you can hear me.
Yes.
Yeah, the exam is no more open book, or it's still open book?
No, it's not open book. It's a non-programmable calculator is the allowed tool for the exam.
Yeah, but in case you are using like question come with the AC code, so how do you know, how can you do, or the question will provide AC code chart?
I will provide the ASCII code if you would need one, yes.
Okay. Thank you.
You're welcome.
And Merry Christmas too.
Okay. Thank you.
Have a nice holidays.
Thank you. Bye-bye.
So I have a question.
Uh-huh.
Will the mock exam be online or offline, just on site, or? I can't hear you.
Now?
Yeah, I can hear you now.
Okay. So the mock exam will be online as well, but my recommendation is if you have the possibility to join on-site, to join it on-site, because then you have more the environment of a real exam than if you're doing it online. The exam itself, the real exam, will only be on-site.
Okay. Thank you.
Welcome. Then bye-bye and see you in the new year.